I want to start by motivating what I'm going to tell you in terms of the generalized second law. So there was a theorem of classical general relativity by Stephen Hawking that says the area of black holes is increasing classically if you assume the energy density is positive. But this led to a quantum generalization. When you turn on things like Hawking radiation, the area of a black hole can decrease, but it's made up for by an increase of entropy outside the black hole. Or you can drop something in and the area grows. So this led Bekenstein and Hawking to postulate what's called the generalized second law. So the way that works is if I have a horizon, which is a null surface, that's the boundary of the past of some future infinite observer, and I take partial Cauchy slices outside, then at least semi-classically, whatever you think about the ultimate nature of the information puzzle for the black holes, in the semi-classical regime, it's uncontroversial that information is lost across the horizon. And so as you evolve up, you're restricting to less information, and we can evaluate the entanglement entropy outside of the horizon. So if we take the entanglement entropy and we add to it a boundary term that's associated with the entropy of the horizon, that's proportional to the area over 4 n-Planck units, this sum is called the generalized entropy. And the statement of the generalized second law is that this generalized entropy is increasing with time, where by time I mean moving up the horizon in this null direction. So this was, there were a variety of partial proofs in the 90s, but essentially my dissertation research was to prove that this holds for arbitrary quantum field theory states. And I proved it for free field theory plus relevant interactions because you needed a formula for the modular Hamiltonian that actually you saw already in Torba's talk. He didn't really mention this in the talk, but the work of Cassini, Teste, and Torba had the side effect that they proved that formula for interacting field theories. So now this thing is proven for any quantum field theory, at least if it flows to a CFT in the UV. But I'm just taking this as motivation at the moment because this generalized second law sort of suggests a way to generalize whatever is your favorite classical result involving area to quantum situations. You say, you take the area and you just replace it with the generalized entropy by adding an entanglement entropy, and then you call it the quantum version of whatever you were talking about before. So that's sort of a research program I've been working on with several people over the past few years. So one quick example, a lot of people like the holographic entanglement entropy, where you calculate the entropy of a boundary field theory by evaluating the area of an extremal surface in the bulk theory. So what do you do if there's quantum corrections in the bulk? Well, building on the first order suggestion, the end of the zero suggestion of Faulkner, Lukowitz, and Maldacena, well, they derived it from a path integral. Netta, Engelhard, and I suggested that to all orders in 1 over n, the right thing to do is just extremize the generalized entropy. That includes a bulk entanglement entropy on one side. This was recently derived by path integral methods by Xidong and Aitor Lukowitz. Another example, and this is what I'm going to be focusing on today, is focusing, yes?
For all orders in 1 over n, don't you have a problem understanding where the surface is?
Yes, and in their derivation, essentially, you have to take the deviation of the surface from the sort of classical extremized area surface really should be thought of as a quantum operator valued thing. But I believe, I'm not sure how much detail they went into in their actual paper about this, but I believe if you think about it as a quantum operator valued surface, it makes sense. But I'm not going to claim necessarily that every single aspect of that has been conceptually understood.
And presumably understanding this well involves also understanding the entanglement of your gravitons, right?
Yeah, and that's an open issue. Anyway, I call it derivation, not a proof, right? So that hedges my... moving on. I shouldn't have gone back. Okay, so another thing that's true classically is that the classical area is focusing, meaning that if I take my area and I take a sort of functional derivative of the area as I push forwards a slice along a null surface, where v is my null direction here, then because gravity is attractive, if I take a sort of second derivative of that in units, so this thing, the rate of change of the area per infinitesimal area, the infinitesimal one's the scripty one, this thing's called the expansion, and the rate of change of the expansion is negative. This just says if matter has positive energy, light rays focus, they never defocus. So, but in quantum field theory, you can have negative energy density that can defocus things. So a sort of natural generalization is to replace this area with the generalized entropy here. Don't ask me why I didn't replace that thing with the generalized. It doesn't make any sense. Just trust me. So this thing we call the quantum focusing conjecture. And one interesting thing about it is if you start with a nearly stationary null surface, and you take the limit as Newton's constant goes to 0, and you look at the part of this as y, the sort of contact piece as y and y prime coincide with each other. You look at the part that's proportional to delta function, you end up with a statement that is defined purely in field theory. It's just a statement about quantum field theory because we're replacing the second derivative of the area part with the stress energy tensor. And then we don't have to think about gravity. So the statement is that the null component of the stress energy tensor, its expectation value is greater than or equal to something proportional to the second null derivative of the entanglement entropy. Now this we call the quantum null energy condition, and there's now a variety of proofs. For example, for d equals 2 conformal vacua with essentially the same people plus Jason Keller, we proved that this was true using light front quantization for a free boson plus any relevant interactions you want. There's a proof in ADS-CFT, and Tom Faulkner and his research group has now proven it for all CFTs that have what's called a twist gap, which is another way of saying that it's interacting. But there's also this claim from people at Berkeley that this thing is actually saturated in interacting quantum field theory. So this thing actually becomes an equality. I'm not going to say anything more about this because it's not my paper, but it's a rather amazing thing if true. All right, that was my introduction. I think I started at 5 after, according to that clock. So, okay. So now I'm just going to try to give a sort of plausibility argument that's almost a proof of why this thing should be true in any field theory. But I'm going to focus on the case of field theories with one spatial dimension. So let's just assume that I have some energy density whose integral is positive. And this is a sort of schematic argument, so I don't care what this energy density really is, but typically we'll want it to be like the stress tensor. So I assume there's a global stability condition. I assume that this energy density can be written as a local function of the fields, which includes canonical momenta, if we're doing this in a sort of standard phase space. And there might also optionally be constraints. But if there are constraints, I assume they're local too. The question now is, can we show that this, from the fact that the integral of the energy is positive, that the energy density is positive? Well, the answer is no. Because, well, let me first say, I'm being very schematic here. So my energy could be a time-like energy or a null energy, and my space could be space-like or null. So when I say we have one space dimension, typically this would arise if we're doing an initial data problem in a 1 + 1 dimensional system. So the energy might really be defined with respect to the Hamiltonian of some time flow, but everything I'm saying, time isn't going to play any explicit role. Anyway, so can we show t is greater than 0? In general, the answer is no, of course, because we have the freedom to add a total derivative term to our energy density. And if I add a total derivative term m prime, then obviously, if my fields fall off fast enough at plus or minus infinity, then it's not going to make any difference to the energy integral positivity. So the best I could possibly do is say that there exists, subject to some improvement term, such that the whole thing is positive, where the improvement term has to be a total derivative. But this turns out to be true. This is now a theorem that I can always find an improvement term. I'll prove it to you right now using what I call the parable of an ant. So we have an ant that crawls along from minus infinity to some point of interest x naught. And she measures all of the fields to the left of this point, okay, at one moment of time. And she's a physicist, so she knows what you do not, which is the specific laws of nature that are expressed in these functions that I haven't actually told you what they are because I'm trying to be general, okay? But she knows what the actual laws of physics are, and she wants to predict what is the lower bound on the energy yet to come to the right of this point. So I'll give it a name. I will suggestively call it m. M is the lower bound on the integral of the energy yet to come, given the knowledge of all fields to the left of this point. Is this notation clear? It's just notation for what I've just said in words. Okay, so 3 things about this. The first thing is this thing is finite because there's a lower bound on it. And the lower bound comes from the stability property. Whatever energy I've measured so far, there's a lower bound from the fact of the energy yet to come that's minus that from the fact that total energy has to be positive. This is, in fact, the only step of the argument that uses the global stability property. Secondly, classically, this is a local function of the fields and its derivatives. And that just comes from its definition, from the fact that all the constraints are local, that even though the ant is allowed to use all the information to the left, if I consider the space of all possible solutions to the right, I only have to glue them to the solutions to the left right here at this point, so my only consistency conditions have to do with the fields right there. And the third statement is a monotonicity property. So there's just a general logical tautology about the world that we don't always think about, but it's definitely true, that anytime you learn more about a quantity, the lower bound on that quantity can only go up. It can't go down. Everyone agree? So the way this works is the ant can travel to the right. She's now learned more because she's crossed all of these fields. So I can write this as an inequality. As the ant learns more, the quantity that is the integral of the energy yet to come can only, given more knowledge, can only be bigger. But I can break that into the energy she's crossed that she knows what is. That's just the integral of t, and the energy yet to come, which is just m of x1. So if I make this infinitesimal, I just conclude that t plus m prime is greater than or equal to 0. And that's what I said I would prove to you. It's a local energy condition. So classically, if there's a global energy condition in one dimension, there's always a local energy condition as well. Now what happens if we try to do the same thing in quantum field theory? Well, quantum systems have a new property, and that's entanglement. Like if I have a quantum spin system, this is it from qubit, so we can think of these as actual qubits if we like. And we could just put in nearest neighbor interactions just for simplicity. In general, it's not going to be true that we can simultaneously diagonalize all of the t's that are the interaction energies between the nearby points. So the vacuum state is some sort of compromise. Each bond can't have its own way maximally. It has to compromise with the bonds nearby to get a vacuum state. So we can express the fact that this is a compromise from one diagnostic of this as the entanglement entropy, which I would define what is, except you guys already know it all, so I think I don't need to. Okay, so we can now do all the same arguments as in the classical case. I've replaced the continuum with a lattice, but that just, that's superficial. Just changes some of the notation. The only thing I told you that's no longer true is the finiteness and the monotonicity are still true. The one thing that's not true anymore is that M has to be a local function of the field. That's not true anymore in quantum field theory, and the reason why is that entanglement is a sort of a non-local phenomenon, and it introduces non-local constraints. So, for example, there's the constraint Strong's additivity that says the entropy of AB plus the entropy of BC is greater than or equal to the entropy of A plus the entropy of C. One of the implications of this is it says if the ant's sitting on a qubit B, the more strongly that qubit is entangled with the stuff in A, the less strongly it can be entangled with the stuff over in C. This is sort of entanglement monogamy that, that most of us know about. But that means if the ant is trying to decide what state there can be at C, it matters that B is entangled with stuff to the left. So it looks like things are going to get much more complicated, but there's a simplification. Even though M is non-local, it's still tightly constrained. One of the constraints is it has to be invariant under any unitary acting strictly to the left of where the ant is in this region A. Why is that? Because acting with a unitary doesn't change the entanglement structure of the situation. So whatever was the lower bound on the energy in C before, if I act with a unitary in A, it obviously doesn't change any of the observables in C, so the lower bound on the energy is the same. So that means that aside from stuff happening right at this boundary point, this quantity M must be a purely information theory quantity. In fact, I can say something more, which is even stronger, which is we can couple it by a unitary to an auxiliary system that I'll call Q. And then we can start with Q and then state that isn't entangled with anything else. We can couple it with a unitary to Q, and then we can throw away Q. The effect of that is we're doing some map. We're acting with some map of rho of A that could map pure states to mixed states. This is now an irreversible transition. And as an irreversible transition, it now follows whatever was valid before I acted, whatever energy on the right was possible before I acted with this map is still possible afterwards because I could just act with the map and that's the state that does it. But because it's not a reversible transformation, the inverse statement is not true. So what this tells you is that the lower bound on the energy yet to come, this lower bound under this map can only go down because everything that was possible before is still possible, but new things may become possible. Okay? So that tells you that whatever this M is, it has the property that's monotonic under these transformations that are called quantum channels if you're in one community. And there are not many quantities that are invariant under these quantum channels, but one thing that is minus the derivative of the entanglement entropy, where the fact that it's invariant under the quantum channels is equivalent to just another form of Strong's additivity that I've written out here. So what this tells you, if I go back to the continuum limit, and I've just changed the notation here to refer to an integral, and now it's the expectation value of T and the density matrix, but otherwise it's the same thing I wrote before. The one step of what I'm going to say that isn't a proof is that minus S prime is the only thing I know of that has the right weight and is monotonic under all of these maps. Okay? So if that's true, then it implies this quantum energy condition that I told you, that the expectation value of T is greater than or equal to S prime prime. And you can actually fix this coefficient in relativistic field theory by using the vacuum thermality. You can just use first order deviations from the vacuum state and the fact that the vacuum is thermal with a given integral of the stress tensor, that's the boost energy, to say this is the only coefficient that's consistent. Okay? Now, since I've been schematic so far, I didn't tell you whether my x was a space-like direction or a null direction, and I didn't tell you whether my e was a time-like e or a null e. This quantum energy condition can actually turn into a relativistic statement in a variety of ways. The most basic one, if I make both of them null, I get the quantum null energy condition, which I was telling you about all the proofs of that earlier, that the expectation value of TVV is greater than or equal to the second V derivative of the entanglement entropy. Or you can get a quantum weak energy condition, which says that the time-time component is greater than or equal to the space-space derivative. Or you can get the quantum dominant energy condition, where I let my two time-like vectors be different from each other. So I have two time-like vectors that are different, and then I take the perpendicular space-like vectors, and that tells me what second derivative of the entanglement entropy to take to get my inequality. Now, if you're not a GR person, you might not know what the classical form of the null energy condition, the weak energy condition, the dominant energy condition are. These are used to prove a variety of things in general relativity classically, but they are what you would get, the ordinary classical forms of these equations, if you just set all these s terms to 0 and ignore the expectation value. That's the corresponding classical energy condition. Like the classical null energy condition is TVV is greater than or equal to 0. So because these second derivatives of the entanglement could be either positive or negative, these statements are not either stronger or weaker than the classical energy condition, because the lower bound could be either positive or negative. What they are, hopefully, and certainly in the regimes it's been proven, is truer than the classical energy condition, in the sense that this holds in all states in quantum field theory, and the classical energy condition certainly does not. This restriction to one space dimension was kind of important, because that's what guaranteed that the ant was sitting at a point of space instead of like a codimension 2 surface in space-time. You could ask, how is this generalized to higher dimensions? Since the QNEC has been proven in higher dimensions, I only have a sketch of what to do here, but I think the point is that you're supposed to start with the average null energy condition in quantum field theory, which is positivity of the integral of TVV along a whole geodesic that goes from minus infinity to plus infinity, and then you do the ant argument restricting the energy yet to come given all the data under a slice. Naively, you might think you'd get an M that depends everywhere on this slice, but you can, but I think the point is that you can have arbitrary jumps of the field theory data anywhere outside of this null geodesic without contributing to the energy. Because by definition, we're only interested in the energy along this blue line. So I believe you can probably argue that the correction term has to only be something associated with derivatives of this point where the ant is. And if you do it at the quantum level, I think you'll end up with the standard quantum null energy condition. So my conclusions are, first, I've tried to argue that at least with one space dimension, every quantum field theory should satisfy some quantum energy condition where T is bounded by the derivative of some quantum information theory property. It's possible it'll be something more complicated than what I was suggesting, but it'll be something, even in a non-relativistic field theory. In a relativistic theory, we now have a variety of proofs that they in fact satisfy this quantum null energy condition. And for interacting theories in d greater than 2 dimensions, it appears that there are now plausible claims that this quantum null energy condition is in fact saturated in every state. That would be rather remarkable, because it would say that you can actually read off the stress energy tensor of, say, a CFT just from knowing its entanglement entropy. So it's an interesting, fascinating connection between energy and entropy. Or I guess I should be saying it in qubit here, but okay.
So, are there any questions?
At some point, you relate this quantity m with the entropy, or you say you conjecture they are the same. But on one hand, the entropy do not know about the Hamiltonian, right? Because it's just, you have, let's say, a chain of qubits, so it would be something completely independent of the Hamiltonian. So,
Well, in the relativistic field theory, of course, as you know, there's a lot of relations between the entropy and the energy. So one way of putting the statement in relativistic field theory is that, so m is then s prime. It's the derivative of s, minus s prime. And the statement that is that the integral of t is bounded below by minus s prime is just monotonicity of relative entropy. The statement that I can't prove but I believe is true is that that bound coming from monotonicity of relative entropy can come arbitrarily close to being saturated, no matter what is to the left of the point.
so somehow is the structure of the modular Hamiltonian what is there, or just that the Hamiltonian is the zero is the minimum of the Hamiltonian? What do you have to put on top of, for example, for a chain of qubits, what do you have to put on top of?
Right, so in the chain of qubits, you don't have the exact under effect. So
Right.
it's possible there'll be some correction to this m, too. I'm not sure. I just
So you
know
have
there
to
must
put the
be some.
input that is relativistic, the thing.
In the relativistic case, I think there's probably simplifications.
Relating to the saturation that you mentioned,
Yeah.
because again it seems like on the one hand you have a Hamiltonian, which is measuring energy in the state. On the other hand, you're measuring the entanglement in that state for some cut across this null surface, and they're related, they're just given equal to each other. That's very surprising.
Yeah, so one way, it looks almost like it should be inconsistent at first. But the reason why it's okay is, if I go all the way back to here, with the definition, if I take an arbitrary second derivative of the entropy, in general, I could take my derivatives in two different places. And that's positive by strong subadditivity. What we're really talking about here is the contact term as I take y equals to y prime. But there's also, so the statement is only that this delta function piece where y equals y prime is saturated, is equal to the stress tensor. The bilocal piece where y is not equal to y prime is not constrained other than by strong subadditivity. I believe this fixes the various obvious counterexamples that one might have in mind. Andy?
Yeah, so just to be clear, so people have used the word semi-classical gravity in different ways. And I guess what you mean just you take n copies of your quantum field theory, rescale Newton's constant, and then expand in n? Is
No,
that
that's
exactly
not
what you mean?
usually what I mean by semi-classical is I start with a background, I turn on maybe just one quantum field, but then I only consider the small back reaction on the geometry, and I'm just interested in expectation values of that back reaction. So my preferred way to derive the semi-classical Einstein equation is to start with the Einstein equation, take the expectation value of both sides, and then use linearity to say that you don't really care about the expectation value of the... So if you go beyond the linear order, you have this trouble that the expectation value of A times B is not the same as the expectation value of A times the expectation value of B. But if I'm only interested in the first order back reaction on the metric, then everything is linear, and that doesn't cause me problems.
So that sounds like that would be nice to think of it as a systematic expansion in a small parameter.
Yeah, and the small parameter is something like h bar g. And assuming h bar, if you want dimensionless, you have to put in like the wave, it's something like the wavelength of your fields is large compared to the Planck scale.
Okay, so if there are no more questions, we thank Aron again.